Okay, so we were taking notes last time, and we finished here, right, with electrical force, and you've done the electrical force lab, and at this point, I'm hoping that you also did the gravitational force lab. At least that's the order that I wanted you to do this in. I'm going to refer back to the gravitational force lab as we go through this. So if you haven't done the gravitational force lab, I would suggest that you stop this part, go finish the gravitational force lab, then come back to these notes. Okay, so we have a little bit more notes to take today than the previous video, which is okay because gravitational force needs a little bit more because there's a couple other things that go along with gravitational force besides just a gravitational field, like things like the difference between mass and weight and gravity on our solar system and lots of other things. All right, so the beginning place for this is that every object that has mass exerts gravitational force on any other object, as long as that other object has mass. Everything exerts gravitational force. Okay, so even you, as you sit here and watch this video, you have a little bit of a gravitational force that is coming from your body. The computer does. The chair that you're sitting, these all have things that have gravitational force. Now, we don't really recognize that gravitational force though, because the force of gravity depends on the mass of that object. And so even though we do exert a gravitational force on other objects, it is so incredibly small that it doesn't affect the other objects. It's not noticeable by the other objects. It's not noticeable by us. Okay. It's so small. If we were massive enough, okay, it would be kind of cool. Like you could take your pencil and you pick it up and you drop your pencil, and instead of it falling to the ground, it literally would start to like orbit around your body, okay, because of that gravitational force that you have. But it doesn't work like that because we are so small compared to what the amount of gravitational force would need to exist for a gravitational field to have a strength to be able to do something like a pencil orbiting around us. Okay, so mass is one thing. And then the other variable that affects gravity is the distance between objects. Okay, those were the two things that you worked on the lab. You did one setup where you were changing the mass of objects, and you saw how that affected the amount of gravity, and then you changed the distance for the second setup, and you saw how that affected the amount of gravity. There is actually a formula for this, okay, and the formula is that it's and we won't do it here in class. Just let me start with that. We're not going to do that in class. That's something that would be in a physics class later on. But there is a force or equation that you could actually use to calculate it. Okay, and it's over here. Can I move this? Yeah, I can. Yeah. Hello. All right. So here's your mass. Here's the mass. Here's the force of gravity, which or the distance. I'm sorry, which is represented by the letter R, and here's the formula. And it's actually really not that complicated. If you kind of look at it, yes, it's a lot of numbers and a lot of exponents or subscripts and things like that, but it's really not that hard. It's literally, if you have the mass of one object and the mass of the other object, you multiply those two and you divide them by the distance between, and you multiply all of that by the constant force of gravity on objects on Earth, which is a number which we won't need to get into this year, but that's how that works. So that if you were ever wondering, that's how it works, and how your simulator did this. Because if you did the lab already, which you should have, it was giving you these answers, okay, based off of, let me move myself again, based off of this formula. The sim just did it for you. It had this mathematical equation already set, so that if you change the mass of the first object, it just plugged that number into this formula. So it completely just worked for you and did all of that math for you, which is why that simulator was so great. All right, so what does that mean about the gravitational field? Well, just like all of our non-contact forces, a gravitational field is where this force is exerted, and anything that has mass has this gravitational field. Like we talked about, though, the mass of that object and the distance between objects depend on how strong that force is. So here's what you should have come up for those answers for the lab, excuse me. All right, so you should have found for the first part that if you had the greater the mass, then you have more gravitational force. So greater the mass, greater gravitational force. Super important concept for you to master for this. Greater the mass, greater the gravitational force. Okay? Like we talked about, that's really hard for us to detect unless one of the objects is really, really massive. And when I mean massive, I don't mean just like a huge skyscraper or a semi truck. Those are big things compared to us. But compared to the universe, those things are tiny. When we're talking about hugely massive things, we're talking about planets, stars, moons. Those are the things that we're talking about where we can actually notice an effect of the gravitational force in a gravitational field with those objects. Okay. The greater the distance between the two objects, the less the gravitational force. And so that should have been for question 2 on the lab that you were able to figure out and answer through going through the lab, is that as you increase the distance away from objects, the gravity became less. Right? So the further away, the less force there was. The closer there was, the closer the two objects are, the more force there is. Okay? And so that's exactly why the moon affects us more than the moon affects the tides of the oceans, I should say, more than the sun does, because even though the sun is much more massive than the moon is closer to us, and so it has a greater effect. Okay. Again, when you guys did your graphs, what you should have seen is that as you get further away, just like with the electrical field lab, it should have been this curved graph. And that curved graph is showing you that it increases rapidly at the beginning and starts to kind of taper off or slow down in how much it decreases the further away you get. And I have that graph here on the next slide that I'll show you. All right. So let's kind of take this then into where we actually see gravity playing out, and that's in our solar system. And so obviously everything is rotating around the sun. I should say revolving around the sun, not rotating. It is revolving around the sun. And that's because it is the most massive thing in our solar system. And so because it is the most massive thing, it has the most gravity, and it's actually able to keep all of those planets revolving around it because of all of the gravity that it's able to exert on those other objects. So what happens to the gravitational pull on the planets as they get further from the sun? Well, if you remember from the previous slide, as distance increases, then the gravitational force gets smaller, so it weakens. Why does the moon have more effect on the tides? Well, I just answered that, right? We talked about it. Even though the moon is smaller, because of its distance being that much closer to the Earth, it actually has a greater effect on the tides than the sun does. Okay. Same thing with you. Okay? You stay on our planet not because Earth's gravity is greater than the sun's. The sun's gravity is greater than Earth's because the sun is much bigger than Earth. But the reason that you don't fly off of Earth and get pulled to the sun is because of the distance. You're on Earth, so you're being affected by Earth's gravity, not the sun's gravity. All right, there's a graph that I mentioned. Okay, this is for the solar system, but it should be a very similar graph that you had with your gravitational lab, because it's doing the same exact thing here where it decreases at a decreasing rate, just like we saw with the electrical field. So it decreases rapidly at the beginning, and then it starts to slow down in how much it decreases as you get further and further away. Although it is still decreasing, it's just at a much lower rate. All right, and that takes us to weight and mass. This is something that sometimes kids get confused with, even adults are confused with all the time, the difference between weight and mass. And the easiest way for me to explain this to you is that we use these words, mass and weight, kind of interchangeably together because we're assuming that you're always on Earth, right? That you're not going to be out on the moon or out at Jupiter or something like that. And so you can kind of use them interchangeably if you are always on Earth, because the effect of gravity, for the most part, is the same. Okay, for the most part, it's the same. So the reason that we have to talk about the difference, though, is because this is science. And so in science, if there's exceptions to this or other places where things change, we got to make sure that we account for all of that, because that's what science does, right? We just can't have one blanket statement for just on Earth, because when we talk about science, we're talking about everything, right? And so technically, mass and weight are not the same thing. Mass is how much matter, the number of atoms, the stuff that makes up an object. So the amount of stuff that makes you up is your mass. The weight is an actual force, and it's the amount of the gravitational force that's acting on that mass. All right? Now, so what we can say is, and one of the reasons why this can get confusing sometimes, is that the weight is proportional to mass. Okay? So in other words, if you have something that is more massive, that means there's going to be more weight. Something that's less massive, less weight. And so it's proportional that way. Okay? But your weight depends on that gravitational field. Now again, we're going to assume that you're going to be on Earth for most of your life. Well, if you're on Earth for most of your life, the gravitational field really doesn't change that much. Okay, the only time it would change would be like, I don't know, if you are really, really high up, like higher than a plane or things like that. Then it changes. Even in a plane, it changes, but it's very slightly. Okay, so for the most part, it's not changing. That gravitational field isn't changing, so the proportion between mass and weight stays the same, which is why we often use those two terms together, but they're not really the same. Okay, and that's because if you went somewhere where the gravitational field was different, like if you did get to go to a moon, and who knows, maybe by the time you guys are adults or in your 40s or 50s, maybe that'll be a trip someday that you guys can go to, is go on the moon. Who knows? But if you could go to the moon, the gravitational field is different there on the moon. And so what that means is your weight would become less because the proportion changes between mass and weight because the gravitational field changes, right? So the moon is about 1/6 the size of Earth. So the gravitational field is about 1/6 on Earth than it is. 1/6 on the moon than it is on Earth. So in other words, if you went up to the moon, the amount of mass that you have stays the same. You're still made out of the same number of atoms and the same amount of stuff. But the force that's pulling on you from gravity is going to be about 1/6 that as it is here on Earth because the moon just isn't as big. Okay? And there's the quote about your mass staying the same. So I hope that kind of clears up a little bit about the difference between mass and weight, and why we kind of can use these words together here on Earth, but how technically they're not the same. And so we need to understand why they're not the same, which is why we took the time to go through that here in this slide. Okay? All right. I hope that you were able to get all these notes done. This is the end of the notes for this week. Okay, so you don't have to turn this document in because as you see, we're going to use this document next week to continue to do notes. So don't turn this document in, but I will be going on and looking at your document to make sure that you've put in every single part of the notes to get your completion points for this grade for the week. All right, as always, I'll be on from 1 to 2 the rest of this week. If you need to talk to me, I have any questions or anything like that. Otherwise, keep working hard, and I will talk to you later.